Okay. So what was going on? We have finite group. And our aim is to describe existentially closed G fields. This meant field with action of G. G is fixed. So what we did last time, we saw that, okay, so let K be a G field. So we noticed that EC implies perfect and strict. Strict meant faithful action. Okay, and now, and also we notice that another thing, that this is complex fields with complex conjugation is a C2 field, but it's not EC. Okay, so now I actually want to describe two more conditions.
What was the
Huh?
What was the I field? What was the I field?
Is there I field?
I mean, what was C2 field?
So C2 is a group of two elements. C2 is the group of two elements.
Sorry, I was another topic.
Yeah. Yeah, there could be actually. Maybe it has a classical meaning which is different, now I'm thinking, but there is something like, yes, so it's a bit unfortunate, but okay. Just filled with automorphism of order 2. Okay, so now third notion, so it was perfect strict. So actually this is the definition which we noticed 10 years before somebody also invented with exactly the same name. So a G field, but it's very natural, is G closed. So it's like algebraically closed, but okay, it's a mixture in this situation. So if K, a G field K, if K has no proper algebraic as a field, G field extensions. Okay, so it may be a bit confusing. If I just say field extensions, it would mean algebraically closed, but it's more restricted. We don't allow this algebraic extension to which the action also extends. Okay, so it's like more restrictive. So actually we will see that they most often they are not algebraically closed as fields. Yes, so that's this remark. Closed does not mean algebraically closed.
Can we say that algebraically closed ones are G closed, right?
Yes, if you have a G, but it is very rare actually. So basically, that's my next comment. Basically, this is the only example. So is it now? So okay, so fact, I guess it's pretty obvious that any EC G field is G closed. Just like easy direction that algebraically closed fields. Okay, so I'll just remove such a statement. If solvable, yes, so if it was not G closed, it will be solvable in extension and not solvable here, which will be contradiction. So if solvable in a G extension, then must be solved in K. Yes, if there was a proper algebraic G-field extension, then there would be some polynomial like this, which has solution upstairs and not downstairs, but that would be contradiction. So that's the third condition, which is necessary. So now let us see that still, okay, maybe two remarks. Yes, as you say, algebraically closed is G closed. So this one, complex number with conjugation, has all these properties and it's still not EC closed. So still something is missing. Sigma is strict, perfect, C2 closed, but still not EC. Okay, luckily there is only one missing. Okay, so the first part of remark. Second part is that if G is finite, then how did I say it? Finite and non-trivial. That then EC G fields are actually never algebraically closed. So I said it a bit last time. Okay. So yeah, the last. Okay, so it has. Okay, I can see quick argument if we believe. Okay, not really what kind of proof. So first part is Artin-Schreier theorem. Says that if K is algebraically closed, maybe some F, G finite, and acts faithfully on F, so let me say just G is a subgroup of out F, then G is trivial or G is C2. That's the Artin-Schreier. You know it? There is such a theorem. It has, okay, in my notes to the Polish lecture, I saw the proof. That takes a bit. Kummer theory, yeah, it's actually lots of, I mean a lot, but some Galois theories used Kummer extension, Artin-Schreier extensions, some work. Huh?
We didn't see that in the lecture, but...
Yeah, so it's not, okay, it's usually not part, but it's kind of good to know that really this kind of automorphism is like the only. Of course, there are lots of other strange ones, which are conjugation of it, but you may think they are kind of the same as the real strange because fixed point will be. Another part of this theorem, maybe I will not write it, of Frattini-Schreier is that the fixed field is real closed, which has, for example, it has the same theory as reals, all this property.
Then, right?
Huh?
What is the fixed field here?
The fixed field of this, okay, so if this is C2, so there is one automorphism,
Then
there is a fixed field, which is then degree 2 extension, but then this fixed field really is like reals. It has all the properties of reals, there is an order, etc. And you can repeat the argument from previous lecture, exactly the argument, showing that then it cannot be, again, it cannot be existentially closed. Okay, so for G equals CT, this, huh?
But we said that C, complex numbers has a lot of automorphisms.
Yes, even of order 2, yes.
And in here, this out F can be very big.
This out F, still there are a lot, okay, but if F is QR, still there are a lot. So smallest option is if F is FP Alge, then it is this Z hat, still cardinality continuum, but kind of very well behaved.
It has a lot of subgroups.
It has a lot of subgroups. All the finite, okay, to understand, yes. So the simplest one, like algebraic closure of prime fields, so it contains all the information about field extensions of this F. So you can think about this. Yes, but it's a bit hard. Okay. But if it has transcendence degree bigger than 0, then also there are lots of things coming from transcendence basis and its automorphisms. And even so this is not a Galois theory anymore, it's just basically any permutations and things like this. And then, so it's very big. Yes, very big, and it always contains degree 2. Now I'm thinking. Okay, in positive characteristic, there is also a little thing. This can happen only in characteristic 0 in particular. If F has positive characteristic, there are no finite group actions at all. Okay.
So G is finite, it's that much restricted. Right?
Yes, so it's already restricted, basically one case, but this case is not happening in characteristic positive.
Yeah, but I was just thinking that the automorphism of C is very big.
Yeah.
I was thinking there must be a lot of finite subgroup of this automorphism group.
Not really, but okay.
So there is no.
I mean, I guess still there may be 2 to the continuum subgroups of order 2. You just conjugate. I have no idea how many, but
they have to be order 2.
Oh yes, only order 2. Mm-hmm. Yes, that's the restriction. Mm-hmm. So the structure, yes. So not everything is, but subgroup, subgroup is what, yes, subgroup corresponds to like subfield, which is very close to your field, okay, by this, so this order 2 means that constants give extension of degree 2, so it means that all the subfields of algebraically closed fields, almost all, are pretty far from it. You don't have finite extension, which is algebraically closed, unless it's like taking reals and complex numbers.
But if this is true, how the inverse Galois problem is a problem? I mean, let us look at Q.
Yes,
Of Q.
but maybe you are confusing Galois correspondence. So finite extensions of Q correspond to subgroups of finite index of yes, this contravariant things, and they are a lot,
Yes, okay.
and not the other way around. So I'm saying for G, C2, F sigma is like C sigma, so not EC. Yes, the Galois correspondence is confusing. So as I was saying, yes, this means there are no subfields close, very nearby algebraically close field.
Okay.
But there are a lot which are on the bottom, kind of. And in the middle too, but not very close. Okay. So as I said, there is one more condition, which I think I will discuss in the second hour, which will finally guarantee this existentially closed. But intuitively, what should it be about? So still, it is not algebraically closed, this G field, which is G closed, but it should be pretty big. Still, it is kind of big. Yes, you just forbid these algebraic extensions. Okay, if the group action extends, it's impossible, you cannot have. So there will be some notion of largeness of a field which is not as strong as algebraically closed, which will be this fourth remaining property besides this, which will guarantee existentially closed. But that will come later. Now more Galois theory. So now immediate aim is describe G closedness. Yeah, okay, it looks like a Galois kind of condition. It's about finite extensions, which something happens. So we want to really describe it Galois theoretically. Actually, it will turn out that we know exactly if we have a existentially closed G field, it will turn out we know exactly what is the absolute Galois group. So absolute Galois group measures how far it is from algebraic closure. There will be full description coming just from this. Says will be infinite profinite group, but fully described by this finite one. And this will help. Okay. So now assume that K is strict G field. Okay, perfect. Just simplifies life. So now let's collect all the information. Okay, maybe some picture. So what we have? We have, okay, and C is the field of invariants. Then by strictness, it was mentioned last time, the Galois group of K over C can be identified with G, this general Galois theoretic fact. So we have like C, K, this is of course algebraic, finite, and everything lives in a big algebraically closed field, which is C-alg. Okay? Algebraic closure of C, of course, it is the same as K-alg. So there are, okay, so we already have this group G, but we also have this big group. So G is this over this, but we also have this over this, and this over this. So several other groups, now infinite. So curly G, I like to write curly, which are those profinite, is the absolute Galois group. So the biggest one. So C-alg over C. Yes, so this is profinite. And then, as always, we have this restriction map. So from this curly G, we have restriction map to the normal G. We just take automorphism sigma here. And restrict it. Okay. It's normal, so it's well defined. Okay, and then if you look at the kernel, what is the kernel of the restriction map? So let curly n denotes the kernel of res. So that's what always happens in this situation. It's a part of Galois correspondence, but it's very straightforward. There are those elements here, such that if we restrict to k, they are identity. So they are automorphisms of CH, fixing point was C. So this is Gal CH over K. Okay, so now we have all the groups on the picture. This is curly G, this is curly N, and this is our G we started from. And of course, it's part of this Galois correspondence theorem, but just because it is onto, this is onto, so of course this over this is isomorphic to G. This also makes sense. Okay. If you have normal closed subgroup of profinite group, then the quotient has natural profinite group structure. But here it's even finite. So this isomorphism is okay, now it's finite, but this always has more structure than group if it was closed and inside profinite. Okay, so sorry?
So it's again a topological group.
Yes, again. So always, yes. Okay, now if you divide by I think it's always topological group, even if you divide by non-closed, but then I think you don't get Hausdorff. Or maybe not even T1, something like this. It's rarely considered because it's pretty strange. Yes. Actually, is it? It even appears in the situation of Lie groups. You have this, but I forgot a bit, closed embedding. Then if you divide by this, you get another Lie group. But you can get crazy things, like in S1, you send what do? Like you pick up some irrational point and start taking its powers. It becomes dense in S1, and if you divide it, it's something crazy. It's, I think, not Hausdorff. And okay. Okay, the theorem. So Kg as above. Following are equivalent. Let me put it in such a way that it is easier for the proof that K is not G closed. So there is a proper algebraic extension which is a G extension if and only if some Galois theoretic property there is a proper closed subgroup here in this absolute Galois group such that yes, so here it is G0, currently G0 in G, restriction map, it still goes on to G by the restriction map. Okay, so such a thing may exist. I will discuss later. This is actually something called contradiction of this being Frattini cover, and this notion is connected to Frattini subgroup, which you may know from group theory. I will discuss it later. So it becomes kind of Galois theoretic group theoretic property, which is very useful. Okay, so let's see proof. I will not say everything, but I will try it. So this is how Galois correspondence work here. So I want to do it, maybe not everything, but quite precisely that we see this connection. So if it's not G closed, how to obtain this G0? So not G closed means there is K prime G field extension, algebraic, well, okay, and proper, not the same. And from this K prime, we should obtain this G0. So how to do it? It's not directly from K prime, so it's a G field, G acts on it. So let C prime be the G invariance of this. Okay, G acts we can take invariance. And curly G0 be the absolute Galois group of C prime. Okay, I defined, but I always recall what it means. This means well, C prime alg, but it is the same as C alg. Yes, everything is inside, is an algebraic extension of C here. So this is the subgroup which comes by Galois correspondence from the invariance of this thing telling you this was not G closed. Okay, maybe on the picture, why not? On the picture, yes, we have this extension here, K prime. K was the whole, K is of course the whole of this. And here, this is the C prime, of course, containing. So this is this G0 in Galois correspondence corresponds to the C prime. So why is it good? Okay, this is Galois theory. So we need to show these two things. First, it's not everything. Okay, so by Galois correspondence, this is a subgroup of G, curly G. Yes, all intermediate fields corresponds to subgroups, but we want to know this is not G, so it will correspond to the fact that this is not the same. And second, that what we wanted here. So let's see it. So as I said, for that enough to see that C prime is properly contains C by Galois correspondence. Okay, and we have this diagram which I already wrote there, but it's better. Okay, so everything is inclusion. But here, Galois groups, here is G, and here is G. Okay, it takes, theoretically here it could be something smaller, but extension of faithful action is again faithful, so it must be really G. Okay, so it means the degree, again by Galois theory, the degree of extensions are the same. Okay, so K prime C prime equals KC. So this is like the same, but this is proper. So this must be also proper because these degrees, you know, their products are the same. So since K prime, we get okay, so such a rather easy thing, but something has to be observed. And the other part, a little bit similar. So for 2, again, a little diagram. We have this G0 in G, just again inclusion. Here we have restriction map. Here we have also restriction map from C prime, restriction map from automorphism over C prime to automorphism over K prime. Okay, we can say this is restriction, this upper restriction restricted to G0, taken here. But here we have yet another restriction map from this field to this field. Yes, if you compose such restrictions, it's okay. But, from K prime, so here if we take, I don't know, some tau, then we restrict it to K. Here if we take some sigma, then we restrict it to K prime, and here, yeah. So one should really say upstairs, downstairs, what is here, but it's too much. Okay, now something, the fact that this, that K prime, that the action of G on K prime extends the action of G on K means that this is isomorphic. This one has to maybe, also not difficult. Okay, so groups are the same. There is restriction map. Okay, I guess maybe it's not necessary since the restriction. No, okay. Yeah, theoretically it could be. It could have some kernel or something. It's not always like this. That even if groups are the same, the restriction will be. But the action extends the other action, so that means it must be really.
G is finite.
G is finite always. Yes, here. So like these elements act the same here and here, so this is isomorphism. And if you can see, this is enough, because now it means that you get everything, so you get all this G here from this G here, and this is onto, has all these restrictions, so this maps onto here. Okay, so everything. Yes, in this paper there were these kinds of arguments, like pretty quickly everything nicely comes together the way it should. So it's the end of one implication. And for the other one, so now we have this G0 and we have to produce this K. So it's kind of going opposite, but the confusing part is that this G0 does not correspond to the field we are looking for. It corresponds to invariance on the action of it. So, as it was before, okay? So this G0 corresponds to this invariance. So it's a bit more thinking, and we really want to define this K prime. So it will not come directly from here, but from something else. Okay, such that okay, and this is actually equivalent to this. Is it? You remember this is a kernel. So if you have some subgroup always in any epimorphism of groups, you have a subgroup here, then it maps onto in the quotient if and only if you take the group generated by this and kernel, you get everything. It is quite easy to see. It will be also used once at the end. Yes, it is normal, so it is really already a group, but it's full. So finally now define, as I said, C prime in the Galois correspondence corresponding to G0. But this thing which we are really looking for, K prime, this will correspond, so it should be bigger field, so it corresponds to smaller group. So it should be this kernel intersected with, in Galois correspondence, should correspond to kernel intersected with G0. Yeah, okay, so then again we need to show so it should be what? Proper, not G closed. So first it is proper extension, of course it is algebraic. Second, it is a G field extension. So there is a G action here which we have to find. Okay, and this G action will be given by a Galois group of this over this. So we have to compute this Galois group, and so actually first I'm showing, so this is exactly this part of fundamental theorem of Galois theory. Okay, so look at G0. So by Galois correspondence, if we go back, G0 is exactly the Galois group of C alg, which is the same as C prime alg. Let me write it like this now. Yeah, okay, C prime alg over C prime alg. C alg. All algebraic closure full are the same here. And this is a normal subgroup. N was normal in G, so intersection is normal in G0. Which by Galois correspondence is Galois group of C prime alg over K prime. So lots of Galois correspondence. Okay, that's how it works. But it's normal. That means you can describe, so then Galois theory, fundamental theorem of Galois theory, tells you that by normality, that K prime over C prime is Galois, and Galois of K prime over C prime is the quotient of this over this. That's the part. Okay, but now either directly from that or from the fact that we have this G0 by assumption. Now we use the assumption here is this onto G, and kernel is of course the old kernel intersected with G0. So by this, this is isomorphic with G. That's how we use the assumption. Now we use the crucial point that still it's mapped onto G. So it's epimorphism and the kernel is this. Or I guess there is, but I always forget, having this equality.
Yeah, I was thinking that.
Probably it also implies already this by second theorem or something, but yeah, let me use something I'm totally sure about. So this.
So it's isomorphic to n G0 over n.
So isomorphic to A G0 over n. Okay, and n G0 is G. Yeah, so it's the same. But this I will use differently at the end. Okay, so K prime is a G field. By this. So, proving partially too. Because of course to say it's a G-field extension, first I need to put a G-field structure here. Okay, actually the second part I will not, what I'm proving now. So now for one, so again, something bad may happen. Okay, there must be inclusion here and it must be proper. So for one, K, as it was written before, is C arch N, somewhere I hope, or not. This is this. Okay, since again Galois correspondence and this. This is Galois correspondence and K prime, so it must be contained into C arch something smaller, fixed points of something smaller and intersected by G0. But still we may be worried it is equal, so we have to know that this is properly contained in this, but this actually follows from this, or it's even easier. Okay, so since what? Since and G0 is G, and G0 is not G, then N intersected with G0 is properly in N. So again by Galois correspondence. So this is giving 1. Okay, and the last part of 2 I'm skipping. So this is proper, this is G-field extension. And again, looking at restriction maps, you can see that this action extends this action extends this action. So that's the full row. Okay, I guess it's perfect for a break. So that's the end for first